Geht? Okay, then let's start, and with a brief recall of the last part that we discussed last week. We are talking briefly about cryptographic primitives and security notions, which will lead us to the concept of trapdoors that we need which we need in public key cryptography and also in post-quantum public key cryptography. So here is a general setup that we already discussed last time. Function families, it's function families is, okay, now it's function families are index sets of functions. The index set is usually called a space, the key space. And for each key, we have a function and a domain and a range, xk, yk. And we say that the function compresses if yk is smaller than in size than xk. And often we have, but not exclusively, although everything can be phrased in this way, we have that k is a subspace of 0, 1 star, usually a proper subspace. And we have polynomials d and r such that d is that xk is at 0 to the d of length of k, and yk is 0, 1 to the r of length of k. Everything can be phrased in this way just by using binary representations for other objects, like sets, numbers, whatever you like. Okay, and then we saw that we have one-way functions, and the one-way function is a function that's easy to evaluate on all inputs. So there is an efficient algorithm that, given a key and an input from key k and an input from xk, outputs the function value. And it's hard to invert even on random inputs, which means for all probabilistic polynomial time algorithms, given a key chosen uniformly at random, and also given the image of an element chosen uniformly at random from xk, so here I assume that xk is finite, A outputs an x prime such that fk of x prime is equal to fk of x, only with negligible probability. So it succeeds in finding a pre-image of this image only with negligible probability. Why do I write this here? By doing this way, I'm guaranteed that a pre-image exists. I don't have any guarantees about f being surjective or fk being surjective or anything like that. And just by this here, I'm guaranteed that there is a pre-image, and I also define a distribution on images, namely the induced distribution by first picking x from xk uniformly at random and then applying fk. Right? And in formulas, we usually write this way. For all probabilistic, PPT stands for all probabilistic polynomial time algorithms. The probability that A given key k and such an image produces something such that fk of this something that it produces is again fk of x is negligible. And in these lectures, I will always then, here is the statement. So what is a property that, the property that counts as a success. So a success is if A outputs something that evaluated at fk yields fk of x. And everything to the right of the semicolon defines the probability space. Here, key chosen uniformly at random from k, x chosen uniformly random from xk, except the probability space, except for the internal coin tosses of A or other algorithms that I use. They are always probabilistic, so the space, the probability space is always defined here, plus whatever coin tosses the algorithms make. And this should be negligible, and I'm not going to define what negligible is. It's the usual term, okay, depending on a security parameter. And collision resistance is similarly defined. Again, it must be the function must be easy to evaluate, and this time we want that for all probabilistic polynomial time algorithms, the probability that A outputs a collision is negligible. And a collision is simply A is just given K as input, a key, it outputs two element X and X prime, and the success is, well, this pair satisfies that X is not equal to X prime, but they have the same image. And here the probability space is only over the choice of the key. And last time we saw that if we look at this function fa, which goes from 0, 1 to the m to zqn and maps every bit string z, say, to a times z mod q, mod uq, that this is one way if the so-called inhomogeneous SIS problem is hard, and it's collision resistant if SIS is hard for those instances. Because if you have a collision here, you can easily get an image or pre-image for 0. Just take the difference of the two images. Those will have -1, 0, and 1s as input, so it will be short. So the beta for which this becomes hard is something like square root of m. Okay? So that's already how this stuff here, and actually our problems, SIS, N, Q, beta, M for appropriate beta, gives us already something that's collision resistant. Okay. But collision resistance hash functions are important cryptographic primitive, but usually we want other more powerful primitives than just collision resistant hash functions. We want encryption schemes, we want digital signatures, among other things. And so I first will define encryption schemes, I will define security concepts for encryption schemes, and then, given those things, we'll go into the constructions of these things using lattices and lattice problems, and that will cover the rest of these lectures for this little course on post-quantum cryptography. So let's define first the syntax of encryption schemes. As usual, a public key encryption scheme consists of 3 probabilistic polynomial time algorithms: key generation, encryption, and decryption, with the following syntactic properties. As usual, first syntax, then security. Gen on input is so-called security parameter 1 to the n, and once, not 1 to the n, which I know is 1, so n once, n written in unary, outputs a pair of public and private key denoted pk and sk. The encryption algorithm on input a public key pk and a message m from some set of messages that is usually determined by the public key. Outputs a ciphertext C, also from some set of ciphertext depending on pk. But then, given the sets, we can usually transform that into bit strings of certain lengths using representations for the elements of those sets. The decryption algorithm obtains a private key sk and a ciphertext C and outputs a message. And for all messages, we want that the following probability is negligible. The probability that we encrypt message M using the public key, using our encryption function, and then decrypt it with the corresponding secret key, but that is not equal to M. So the decryption of a ciphertext for M does not give us back M, the original message. That should be negligible, and here's the probability experiment. It's over the choice of the key pair. So there may be key pairs for which this is wrong. for which there is a significant probability of the decryption not working correctly. Okay? And in many courses, we'll see here that we want that the here with equality is 1. So this inequality, the probability for this equality is 0. For lattice-based encryption schemes, this does not work. We need to allow a decryption error. Usually, there are a few things. Well, you can define things that are insecure that does it, but I don't know anything with secure which allows for this, for a 0 decryption error. I don't know. I don't know a single scheme, I think. They all have something in there. Okay, good. So this is the syntax of a public key encryption scheme. And then we'll talk about the security. And for security, I will first define adversaries that we consider against public key encryption schemes. And an adversary against a public key scheme consisting of our 3 algorithms is a pair of probabilistic polynomial time algorithms, A0 and A1, with the following properties. A0, on input a public key, outputs a pair of messages M0, M1, and a state. And A1, on input a public key PK, 2 messages M0, M1, and a state ST, and a ciphertext C outputs a bit B. So you can also view these things as the A0 as A1 as an algorithm that works in 2 phases, or actually an interactive algorithm that talks to something else. It has 2 phases. In the first phase, it's A0, and the second phase is A1. And the state is just there to remember what it did in the first phase. For example, collect all the random coins that it used in the first phase. That usually is good enough. That is good enough, because once you know the random coins it used, it's deterministic. You could rerun it again just to see what it did in the first phase. Okay, these are just adversaries. So in the first part, we output a pair of messages and a state. That's just to remember what it did. And in the second part, it outputs a bit. And what we want for a public key encryption scheme to be semantically secure, or int CPA secure. Int stands for indistinguishable, and CPA stands for chosen plaintext attacks. If for all public key adversaries A0, A1, the following probability is negligible. A1 outputs a bit B over, and now this probability is over the following probability experiment. The key pair is generated by keygen. M0, M1 here is generated by A0. B is chosen uniformly at random from 0, 1. And the C that A gets here is the encryption of message MB with public key PK. So what this says is, in the first phase, so the keys are generated correctly, and then in the first phase, A0 may pick any pair of messages it likes, M0, M1. It then gets A1, or in the second phase, we get the encryption of a random element of the pair, and then we have to check or decide which pair we got. And if we do that correctly, then this event would be 1, and this says that for all pairs of algorithms, the probability that this is successful should be negligible, must be negligible. Okay? Okay. Usually, and I didn't put that in here, we have restrictions, little small restrictions on the M0, M1's pairs that A0 can output. Typically, same length, but I didn't put it in there because usually our syntax of public key encryption schemes already guarantees that, because they all must come from the message space determined by PK, and those usually have the same length, if appropriately defined. Okay, this is for public key encryption schemes. This is the weakest form of security, since we do not include anything about, say, chosen ciphertext security. Although in the talks in the seminar, we'll see something about chosen ciphertext security. Okay. This is the standard definition of semantic security for public key encryption schemes. Yeah. Good. So this says that you cannot, even if you cannot get any information about a message from a ciphertext, because if you did, you should be able, since you can't pick those messages yourself, you should be able to distinguish them. That's the intuition behind this definition. Okay, then, so as I said, stronger security notions like in CCA, under security under chosen ciphertext, are considered to be appropriate. And those can be actually achieved from semantically secure schemes as defined above by generic transformations, for example, the so-called Naor-Yung paradigm. Although if you want to achieve efficient schemes, you often take one of those schemes, you start out by this generic transformation, then you tweak the generic transformation and adapt it to the specific scheme that you have there to make things more efficient. Okay. So this is our first, this is public key encryption schemes. Then we'll want also to work with signature schemes. And signature schemes, again, consist of 3 probabilistic polynomial time algorithms. This time the syntax is as follows. The key generation algorithm has the same syntax as for public key encryption schemes. It outputs a pair of PK and SK of public and private key. The signing algorithm on input, a private key SK and a message M. Now the signing takes a private key and a message, outputs a signature. And again, the message space and the signature space may depend on the public key. Here, as usual, I assume that given one of the two, you can at least check what the other should be, whether the other one is the correct one. You may not be able to actually compute it from it. Sometimes I will even assume that you may compute it from it. Okay, so you compute signatures on messages using the private key, and verify gets as input a public key, it gets a message and a signature, and it outputs a bit B. And again, we want a correctness condition, and we want that the following probability is negligible. We generate a signature on message M with a private key SK, and then verification on the signature with the message M here, the corresponding public key, still outputs not 1. That should be negligible. So usually we assume that verify has 2 outputs, 0 and 1. 1 stands for I accept the signature. 0 stands for I do not accept the signature. So that we do not accept correctly computed signatures using the correct public key, that should be negligible. The probability here is over the key generation here. And it may also, since these are algorithms, it may also be over the internal coin tosses of sign and verify. Sign usually uses randomness, verify usually doesn't use randomness. This here in the public key setting, encrypt usually uses randomness. Decryption usually doesn't use randomness, and hence here also the randomness of the probability is also over the random coin tosses of the encryption algorithm. So correctness for signature schemes means that correctly signed computed signatures will be accepted with overwhelming probability. Now, what do we want from the security? Again, we do that by first defining adversaries. What is the syntax of adversaries? So as an adversary against a signature scheme, gen sign verify is this time a single probabilistic polynomial time algorithm, but it does have oracle access to sign. And I will explain what that means. And A on input a public key outputs a message M and a signature sigma. And what does it mean to have oracle access to sign? A can query adaptively for signatures of messages MI with private key SK, corresponding to the public key that it gets as input, but it doesn't get the private key. And that means here on query MI, A receives in one step, so it doesn't count, basically, sigma I, which is a signature of MI using the secret key SK. And for the security, we also need the set Q, in which we collect all the query messages of A. And then we say that a signature scheme is unforgeable under adaptively chosen message attacks if for all signature adversaries A, the probability, that A computes, given the public key, computes a message signature pair where the keys pair is computed using the key generation algorithm. So it computes such a pair that is accepted by the verification algorithm, and M was not one of the messages that was originally queried by A. This must be negligible for all adversaries A. So it can compute a signature on a new, it should not be able to compute signatures on new messages. No? Except with negligible probability. Okay. This is the usual unforgeability definition. And there are weaker notions, there are stronger notions, both are possible and useful. The weaker notion is usually called, and we'll see that in some talks at least, static message attacks. The query messages have to be chosen by the adversary before the key generation algorithm. So here it picks the set Q, and then we may actually generate the key depending on the messages. This is something that's very useful in security proofs, or also in constructions. Makes life much easier. And there is a standard way of boost the security under static attacks to adaptive attacks as defined in this definition here, and that uses so-called chameleon hash functions. Hash functions that sort of pretend to be hash functions, but in fact are not true hash functions. And there is another, so what we'll see is often in the lattice setting that we first construct something under this weaker notion, and then we'll use these chameleon hash functions, which we can also construct using lattices, to get security under adaptive attacks, which is usually what we want to achieve. There's also a stronger security requirement, which is called strong unforgeability, in which we consider a new signature on a query message as a valid forgery. So in the original definition, we require that the adversary outputs a signature on a new message. in the stronger security setting, it is allowed to either output a signature on a new message or a new signature on an old message. So by this, we also, this thing here allows to modify signatures on old messages. So if you get a signature, then you can, from that, compute a new signature. That is not a breach of security here. It is a breach of security here. Okay? So this is a stronger definition. It forbids more. And that's usually getting from here to here, from adaptive to strong security, it usually is not such a big deal, actually. Okay, so this is this one. So these are the things that I want to consider in these lectures. In the talks, we'll see other things as well. We'll see identity-based encryption. We'll see attribute-based encryption. We'll see homomorphic signature schemes. We will not see homomorphic encryption, but those can also be defined using these things. Okay, so this is the sort of the basic security primitives with which we want to work in these lectures. Now I want to look at a standard way of defining signature schemes to see what we need for lattices in addition to what we already have. So far, we just defined lattices, we defined lattice bases, we've had these seemingly hard problems for lattices. We had these interesting lattice problems, SIS, LWE, where SIS already led to some interesting cryptographic constructions, namely hash functions, collision-resistant hash functions, and one-way functions. But we want to do better than that. Signature schemes, if you know a little bit about constructions of signature schemes, you may know, okay, signature schemes we already know how to construct from lattices, right? We know how to get one-way functions from lattices. Once we have one-way functions, we know how to construct secure encryption schemes, secure signature schemes. We need for that one-way functions and collision-resistant hash functions. Bingo. We have both of them based on SIS. Unfortunately, those constructions, those generic constructions, are very inefficient. So we want something better. And then from that abstractions, we'll see what kind of additional stuff we need to get to efficient lattice-based signature schemes. There are other ways to achieve lattice-based signature schemes, but I don't think we'll see those in this seminar. Do we see signature schemes without trapdoors? Okay, good. Then we'll see them in this seminar as well. Okay, let's look at the currently still most important construction of signature scheme, which is called the RSA full domain hash. I'll just do it very briefly. What is the RSA full domain hash doing? It's a variant of RSA signatures, which in the textbook way are highly insecure. So here our key generation algorithm generates PK and SK in the following way. PK consists of three things, N, E, and H, and SK consists of N, D, and H, where H, N, and E are integers, D is also an integer, and H is a function from 0, 1 star to Zn. It's a hash function. And N, E, and D are natural numbers such that E times D is 1 modulo phi of n, where phi of n is Euler's totient function, namely, so phi of n is defined to be the size of all of the is a number of integers in Zn that are relatively prime to n. And we want then that E times D is 1 mod 5. And usually, you remember that usually n is P times Q, P not equal to Q, P comma Q primes. In which case we know that phi of n is equal to P minus 1 times Q minus 1. Oh. Okay. And then to sign a message with secret key sk, what you do is you first apply the hash function h to m. That gives you an element in Zn. And then you raise this element u to the dth power, modulo n. And that's your signature. And to verify a signature on a message m with public key pk, you again compute h of m. You compute sigma to the e, where e is part of your public key, and the condition is that you output 1 if and only if sigma to the e is the same as h of m. And the correctness is based on the usual thing. We know that for all a in Zn, n is equal to p times q, p comma q primes. P is not equal to q. We have that a to the d to the e is equal to a modulo n, if d and e satisfy the condition as in our key generation. Okay. So what you can see here is, okay, well, I'll explain that later in more detail, maybe. Okay. So this is the usual stuff. This is called the RSA full domain hash. We usually assume that in our security proofs, we usually assume that H is a random oracle. Actually, in our security proofs, we assume that, period. In practice, we replace H by a collision-resistant hash function. Let's look at the generalization. And that's where I also want to tell you how we can view this. So in the generalization, we use pk, or pk is a description of an element fpk of a one-way function, of a family of one-way functions. And we have a trapdoor td. So in our case, RSA, fpk is f of n comma e. It's a function from Zn to Zn. So that would be x, k, or pk. This here is y, pk. And it maps an element x to the e mod n. Okay. And our function family would consist of all these things here for appropriate n and e from the natural numbers. We also have a trapdoor and an appropriate hash function. And the trapdoor is part of the secret key, and the trapdoor TD allows you to invert FPK. Okay? Okay, so that's what I denoted here. So basically you can see TD as a description of, again, a function. Okay, so TD of FPK. In general, maybe this thing doesn't need to be invertible, doesn't need one-to-one or injective, then this means pick any preimage. And then what we do here, and that's so on input PK, so on input MSK, I switch the order here, doesn't matter. As before, we compute the hash function. This hash function, I assume, let's do that here. The hash function, I assume, goes from, say, 0, 1 star to xk. Yk. Or ypk, whatever, ypk. So I map M using the hash function to an element of ypk. And then using my trapdoor, I can apply the inverse function of fpk. So I compute a preimage for u under fpk. So and then verification does the obvious thing that applies fpk to sigma and checks whether this is h of m. So here pk is n comma e, fpk is defined as here, the exponentiation with e, the trapdoor is this d, the inverse really here exists because here we see that the exponentiation with e and exponentiation with d are inverses to each other. And so what you can view here is, well, you map M to some element in this ypk, and then you sign it by proving that you know the trapdoor, which allows you to compute a preimage, which allows you to solve a difficult problem, namely compute a preimage for this element u that depends on M. Because if you construct signatures, you should be able to do something depending on M that on an SK that you cannot do without knowing SK, hence proving that it was you that signed the messages, that authenticated this message. Okay. So this is the first generalization. We'll go even one step further in generalizing this. And that the step further will mostly deal with the case that we do not have injective functions here in general. In RSA we do, but if we use lattice-based stuff, we usually do not have injective functions. Okay. So what are the requirements that we have here? So obviously, we need to be able to generate trapdoors efficiently. Otherwise, the key generation algorithm is not efficient, and we always need these things to be efficient. Yeah? So that's the first thing. The second thing is now, when we go to how do we prove the security of these things? To prove the security of such a thing, here or here, what you usually do is, given any forger that is able to forge a signature or to compute a forgery with non-negligible probability, you turn that, you want to use that to design an algorithm that violates the one-wayness of our function family, that can invert. So you need a reduction from a forger to an inverter. Okay, and so this is what I say here. The forger must lead to inverter for one-way functions. Now, here we have the usual problem that we have when, or the usual problem that we have when we do that is the forger has access to the signing oracle. An adversary against the one-way function does not have access to an oracle for the one-way function or the inverse of the one-way function. So we must use that forger that will ask us the reduction for signatures. We must be able to tell the forger signatures without actually knowing the trapdoor. So obviously, something strange must go on here, because we must be able to construct these signatures without trapdoors, but the whole signature scheme is, well, without trapdoors, you should not be able to construct signatures. So what we do here, we do something that looks like signatures, but they are not really signatures, or we construct pairs in a different order. Okay? And that means that we must be able to generate pre-images for F with distribution close to the distribution of signatures in the signature scheme. Which in the RSA case is, these distributions are easy, right? Because in the RSA full domain hash, the image here, if we model the hash function as a random oracle, this U here is distributed uniformly at random in Zn. That's what we require from a random oracle, independent of M. It's distributed uniformly at random. Now these functions here, exponentiation with E and D, are one-to-one functions. Okay? So if I generate here an element uniformly at random and apply a one-way function to it, sigma is also uniform random. So I need to be able just to generate uniform elements uniformly at random. Well, I can do that. Okay, there is several difficulties in there. I won't go into the details of it, because you should be able to generate pre-images, but on the other hand, we want to break the one-wayness, so you should not be able to construct pre-images. So there is this game going on that for some things you can create pre-images, the things that the adversary queries you, but then for the other things, the things that you're really interested in, the pre-image for the thing for which you have to compute a pre-image, that should not be able. You usually do that by combination of two things. Often you generate public keys and trapdoors in a very specific way. And the other is you program the hash function. You cheat with the hash function so that it still looks like a hash function, but you have additional knowledge. In the RSA case, let me be a little bit more specific. In the RSA case, what I do, the hash function h of m, what I do is I pick x uniformly random from z, and then I set u to be x to the e mod n. And that's my h of m. Uniformly distributed uniformly at random. But the interesting thing is, if now somebody wants me to give him a signature for this thing, I can do that. It's x. I know it. Okay. So, but then you have to be, to actually invert it, you have to be lucky. And yeah, if you're interested in the proof, go to Foundations of Cryptography, where we'll cover that. Right? So we have to play around with these things. And we can, as I said, we can abstract even further and generalize even further from this here to the case where we do not necessarily have injective or one-way function, one-to-one functions, sorry. We will have one-way functions, but they are not necessarily one-to-one, which are two completely different things. Okay? And that leads to pre-image sampleable function families. But again, before I do that, recall I need trapdoors here. Trapdoors is something that we generally do not have for arbitrary one-way functions. So what we really want for these constructions are trapdoors with certain, for one-way functions with certain properties. Now, even more general way of looking at this process or this thing to construct secure signature schemes is as follows. We use these pre-image sampler function families, and such a family is defined as follows. There is an efficient probabilistic algorithm that samples keys, the indices for the elements of the function family, together with trapdoors TDK. So the trapdoor belongs to key K. There is not one trapdoor. For each key, there is a different trapdoor. And that's done according to some distribution determined by a security parameter 1 to the n. And we assume that from TDK we can efficiently determine K. That often is the case. In our setting, it will be the case. And then there exists an efficient probabilistic algorithm, which I denote by f to the -1, that gets as inputs pairs consisting of a trapdoor and an element y to the yk. Or I should, yeah. Okay. And I denote this usually, so if I fix TDK, then I denote this thing here as a separate algorithm. In fact, I denote it as a function, although it's not a function. This I denote by f TDK to the -1. Okay. So, so now for all these things, for each key, we assume there exists an efficiently sampled distribution dk on xk. So there is an efficient algorithm that, given k as an input, samples according to this distribution. It must be a probabilistic algorithm, such that the following distributions on pairs x, y in xk times yk are indistinguishable. Statistically indistinguishable. So no, whatever indistinguishable means that no algorithm can tell the two distributions apart. Whatever, you can formalize that. So the first distribution is a so-called forward distribution. You pick x uniform according to the distribution dk from xk, and then you apply fk on x. That's a forward direction. Okay. Here, this would be the forward direction. You pick x in the RSA case. You pick x uniformly at random. So gk or dpk is the uniform distribution, and then you apply x to the e. That's a forward direction. And the reverse direction is you pick y uniformly at random from yk. So here there's no distribution specified. That means it's a uniform distribution on the set here. Okay? And then I apply the inverse operation with trapdoor TDK on y. So in this case, this would be, I pick y from this element, from this set here, again Zn, and apply x, the dth exponentiation with d. Okay? And these two distributions should be indistinguishable. In the RSA case, they are even the same. Okay? In both cases, they are the uniform distribution on pairs. Uniform distribution on pairs where one of the components determines completely the other component. You can either say this is uniformly at random and then this is fixed as the eth power, or you pick this uniformly at random and then this is fixed as the dth power. Those are the pairs. They are not independently distributed. One completely determines the other. Okay. And then we can define the pre-image sample of a function FDH. So we just have some function family that is pre-image sampleable, and then we do the same thing that we did with RSA. We generalize as follows. So the key generation algorithm generates as public key k and h, as private key tdk and h, where h is a hash function from 0, 1 star to yk. The signature, as before, h to the m, and then you apply f tdk to the -1 of u. And the verification, you apply fk to sigma. And that's it. Okay. But this here now is an algorithm. It need not determine a fixed element. But this one must have the appropriate property down here. Yeah. And this pre-image sampleable gives us much more flexibility because we allow here things that are not necessarily uniform. And in our case, they will not be uniform. Here, I will insist on it being uniform. That's because I want to use random oracles. Okay. Okay, and that's it. So we want to construct these pre-image sampleable functions, and moreover, we need trapdoors. We need trapdoors for lattices in some sense. We need them also for public key encryption schemes. As I said, there are constructions of lattice-based signature schemes that do not use trapdoors, but are still much more efficient than the generic construction of signatures from one-way functions. And they use a similar blueprint, actually. They just get around this trapdoor thing. But need something else instead. Okay, good. So then, then let's go to trapdoors for lattices. Here they come. And I will give you today a somewhat general outline, and next time I will go into one construction of trapdoors in more detail. Those turned out to be very, very useful. So lattice trapdoors. So trapdoors are these things that allow us to invert, in some sense, functions that we defined using lattices. So, for example, these things here. Remember, behind this construction, there is a lattice, namely this lattice lambda A of perp. Here there was this lambda perp of A, which consisted of all Z in Zm such that A times Z is 0 mod Q. And we have here this function family, which is this guy here. We also saw that if we look at LWE, we also have a lattice involved, namely lambda of A, and there's also a function involved there. But we mostly use this here. For reasons, we only need something for this, for reasons I will explain. That has to do with dual lattices, which we'll come to at some point, hopefully. So what I will do is we describe two different types of trapdoors for lattices. The first one, short bases that can be applied to any lattice. The second one, gadget-based trapdoors, applies mostly to the lattices of the form lambda perp of A, as we saw in combination with SIS. And both trapdoors allow to solve various lattice problems efficiently. The bounded distance decoding problem, SIS, ISIS, the inhomogeneous version of SIS. And we'll see, and that will be part of what I tell you in 2 weeks, sampling from so-called concentrated Gaussian distributions on lattices, on cosets of lattices. Those will be basically our inverse functions. Okay, here is, as I said, so this thing here, the short basis you can define for any basis, for any lattice. But when we want to generate them in our key generation algorithms, we still restrict them basically to the quinary lattices that we saw before. Okay. And this is the main result concerning short bases for lattices. It's due to Aitai and Peikert and Michancho and Alven. It's a long series of papers that eventually culminated in something that I tell you in more detail on the next slide, because here's something that's still vague in there. So what they showed is there is an efficient randomized or probabilistic algorithm that given n, q, and m in the natural numbers, such that m is at least c times n times log q for some universal constant c. So it does not depend on n, q, or m, or any subset of the three. And it outputs a nearly uniformly random matrix A in Zn, Zqn times m, almost uniform, not quite, specifying the lattice lambda perp of A, along with the basis S, which is in Z to the m times m of lambda perp of A, whose vectors have norm, Euclidean norm, bounded by an expression that's polynomial in n and log q. Okay. So they generate lattices together with bases and do that for almost any base, any lattice. What this algorithm doesn't do is pick a uniformly at random and then try to find a short basis. If you want to do that, you have to solve the approximate versions of the shortest independent vector problem, which we don't know how to do. So that's why they proceed differently. In parallel, they construct the lattice and the basis. So it's not a separate process, first one, then the other. It's really, you construct sets S, but what you get is that it corresponds to almost all matrices. Okay? There are a few A's that cannot be output by the algorithm, but other than that, everything appears as it should be. Yeah? So the best bound for the length of the basis vectors that one can achieve today is n to this 1/2 plus epsilon for epsilon positive arbitrary. If you want a very, very small epsilon, the runtime goes up. But as long as epsilon is constant, the running time is polynomial. And this is obviously m. Your m is, say, assume it's c times n log q, and then this is polynomial in n and log q. Okay? Compare that to the trivial, easy to achieve, and completely useless bound on the length of basis vectors of q. You can, because, or well, actually q is not even the right n times q or something, or m times q. You can always just find here, find a basis for the kernel of this matrix, modulo Q. If Q is a prime, it's easy. It's a field, then you can do Gaussian elimination, but those elements will all have entries from ZQ, arbitrary. So they will be of size roughly Q or something like that. So you get something that's bounded by Q or M times Q or square root M times Q or so. And that's completely useless for cryptography because it's easy to do. But also for other reasons. Okay. So this is much, much better than this because this depends only on log Q, not on Q itself. Depends polynomially on log Q, not Q. Well, if you have a short basis for lambda perp of A, we have already solved SIS. Take the shortest basis vector and output that. It's a solution to SIS because SIS is exactly here. Find something that's 0. A short basis also leads to efficiently computable solutions for the inhomogeneous version, as we'll see. This is slightly more complicated. This is more complicated. So with these things, short basis, we have SIS, period. And from that, basically, given that, we could almost immediately construct a signature scheme, which I will do actually later in these lectures. Okay? But it doesn't yield us very efficient encryption schemes. And that's why we look at the it also tells us, once we have a short basis, I was wrong. It also tells us how to solve LWE in the search version. Okay? Even in the search version. And let me tell you how we do that. So what we want to do is we actually solve BDD, the bounded distance decoding problem, or search LWE. I will explain it with search WE, but you can do that actually for many other lattices as well. Okay? Good. So remember that in search WE we have this vector S, and we get samples of inner products of S with other vectors, which we modify a little bit by adding an error term. And we write that as we get a vector B transpose, so it's a row vector, by multiplying S transpose with a matrix A. In the matrix, the columns of the matrix are the vectors for which we compute the inner product. And each entry is modified by adding this error term. And the errors are collected again in a row vector E transpose. Yep. Now we are given such a thing and we want to compute S, or S transpose. And we are given a short basis S for lambda perp of A. Okay? Given such a thing, what you do is you compute YT, which is BT, B transpose times S. Now let's see what that is. B transpose is S transpose times A plus E transpose. You multiply that with S. Now this is S transpose times A times S plus E transpose times capital S. But S is a basis for lambda perp of A. So every column of S is an element of lambda perp. So this here is 0. This is a 0 matrix. Since S is a subset of lambda perp of A. So what remains is that this is actually E transpose times S mod Q. And I compute all these things mod Q, because this part here, that this is 0, only is true if I take this mod Q. That's not true if I do it differently. Okay? So I do that. Okay? Now I compute the inverse of S. S is a M times M matrix. And I can compute an inverse of this matrix, but I do that over the rational numbers. Also, the inverse over the rational numbers will exist. It's a lattice. Must exist. Okay. And then this guy here, YT, Y transpose, it's an element in that Q to the M. Okay. So each entry of Y transpose is an element of ZQ. Every element of ZQ has a representative lying between minus Q divided by 2 and plus Q divided by 2. The centered set of representatives. So I compute this representative of this thing here, and then I compute Y bar transpose times S to the minus 1, again in the rational numbers. So I try to get rid of this. Remember, this is Y transpose times S. Y transpose is B transpose times S, which we know that E transpose times S. So here now, I pretend that no mod Q is standing there. So I just do it with the inverse of S. Hoping that this gives me ET. If I have E transpose, I can subtract it from this vector here, which leaves me with this guy here. But if I have so I remove the error. I compute the error. And if I don't have the error anymore, then I can compute the S, the solution, using Gaussian elimination. So I compute a pre-image of under A of this vector here, which I hope that this guy here removes the error. Yeah? Yeah? Okay. So why should this work? So in general, it cannot work. Here I do everything mod Q. Here some things I do mod Q, other things I do over the rationals, and these things simply do not fit very well together. Okay? Except if I know that this element here, E transpose times S, is so small that this modular operation never takes effect. It's right there, but it never takes effect, because everything I do here, if I do this over the integers, everything stays in this interval between minus Q half and plus Q half. If that happens, then I can do all these things and nothing goes wrong, because wherever I need to use the mod Q, I don't need to use it because numbers are just small enough. Now if you add two things in modulo Q, you only take the mod operation if your result is larger than Q. Then you have to do this mod to get into this interval. But if this is small enough that this never happens, then all this is correct. And you will get back the correct error term. Okay? Hence, this whole thing is correct if this here is actually in this set without taking the mod q, but looking at it over the rational numbers. Yeah. Huh? Now, why should small s help me, or a short basis? Well, S times E transpose, what is this? It's again the inner product of E with all columns of S. Right? It's the inner product, so it's E, the inner product of E with S1, the inner product of E with S2, the inner product of E with Sm. Huh? And I want these things to be short, but I know that this thing here, the length of an inner product over the integers by Cauchy-Schwarz is less than the length of E times the length of Si. Yeah? Now this is short by definition, by definition of our chi with high probability. So with high probability, short due to distribution chi in LWE. This here is short by shortness of basis. And if these things fit together nicely, the length of this here with high probability, the length of this here, then this should be in this interval with high probability, which will give me with high probability the correct S. So I will have solved LWE with high probability. Huh? So that's why the shortness comes into play, and that's why we also need here that the error terms that we have in LWE should be short with overwhelming probability or significant probability. Then we can do this thing of ignoring mod q's. And that's a typical thing. Again, you will see that in many things. Make sure that you can do something over the rational numbers because things have been so small that modulo q operations never took place. So with a short basis, we can, as I said, we can do this BDD. We can use SIS, ISIS, I didn't tell you so far, and also Gaussian distributions is possible. I will tell you that when we come to Gaussian distributions. Turns out that all we need is a short basis. Okay, so this is the first type of lattice trapdoors, short bases. Those were the traditional way of defining trapdoors for lattices until 2008 or so, 2009, 2008. And then there was another construction which turned out to lead to slightly better parameters, and it turns out to be also nicer. It's simpler, it's nicer, it's more elegant, and it goes back actually to constructions from coding theory. It's actually what's behind this are so-called systematic parity check matrices. That's all there is to it. So it's a standard construction in coding theory, transformed or transferred to lattices. Or actually, if you look at lambda perp, it's systematic parity check matrices, or systematic generator matrices if you look at lambda of A. At least that's one way of viewing it. Okay, so these are called gadget-based trapdoors. And I will explain these things in more detail next week. Today, I will just give you a short hint what these things are. What we define first for these trapdoors are so-called gadget matrices. Basically, it's one matrix for each parameter set, which live in ZQ times n ZQ n times W, where n and W are suitable parameters. W in particular is a certain parameter. And for these gadget matrices, SIS and ISRS and LWE, ISRS are easy to solve. You will all recognize these matrices, or you have seen them before, although maybe not in this formula, but it's just computing bit representations, going back and forth between bit representations in the easiest case. So for these things, we can solve SIS and gadget matrices. And then we show how to hide these gadget matrices in other matrices, A, that are in ZQ n times m. So they are in there, but they are hidden. And they are hidden in there by using a so-called gadget trapdoor R. And what this does is this gadget trapdoor, if you want to solve SIS or LWE for A, using the gadget trapdoor, you can basically transform that problem of solving SIS or LWE for A to solving it for G. Take that result that you get for G and get it back for A. Okay? Without this gadget trapdoor, you have no clue where is that stupid G in there. Okay? So these things can sort of unhide the gadget G. And we show how to construct almost uniform matrices with gadget trapdoors. That is similar to what we had here, where we have short bases for almost uniform matrices A. And we need those almost uniform matrices because those A's will be public keys. If those public keys are not uniformly distributed but concentrated on some small set, your system is doomed because you have just few public keys. Try them all or get something that's much better than exponential time. So we really need to get these things uniformly at random, mostly. Yeah? So that's something that we can do here as well. And it turns out that this, and here M, W, and M are suitable parameters. So you see here the A is n times M, G is n times W. There is a certain relation between M and W. Okay. And what the parameters are depend on what you want this trapdoor to use for. Depending, it could be on the signature scheme, identity, and now comes the nice thing. With these gadget trapdoors, you can do amazing things. You can do all at once. You can not only do encryption, you can do identity-based encryption, you can do attribute-based encryption, you can do homomorphic encryption, you can do homomorphic signatures, which are often not known to be constructible with the short basis trapdoors. So they seem to be much more powerful. Yep. And it turns out that often we're going. Okay. The one thing that I should remark is once you have such a matrix A for which you have a gadget trapdoor R, you can also compute a short basis for lambda perp of A. So these are at least as powerful as the short basis trapdoors. But often these constructions here, they don't go through short bases, but they use directly the gadget and use properties of these gadgets. And what these gadgets are, I will explain next time, and also see how we hide, how we unhide. And I will not really tell you how to get SIS and LWE, but it's not. Some things are difficult, others are not so difficult. I will probably do SIS. That's not so difficult. LWE is more, and in particular, Gaussian distribution that needs the one has to be very careful in that setting to do that. Okay, and that's it for today, unless there are questions, remarks. The video cannot ask questions, I guess. Okay, good. Then that's it, and we continue next week, same time, same place. Good.